Hello friends, dear learners and my dear student. First of all, I take an opportunity to welcome you at my T.Y.B.Sc. Analytical Chemistry class. I am Dr.S.R.Labhade, working as Associate Professor in the Department of Chemistry at Continuum College, Nashik. Student, in today's lecture we discuss the instrumentation of flame atomic absorption spectroscopy. In previous lecture we discussed the principle of flame atomic absorption spectroscopy. Under this study, we discussed that flame atomic absorption spectroscopy is a branch of atomic spectroscopy in which sample is converted into gaseous state atoms by thermal energy and excited by using their own resonance line. The decrease in radiant power of this resonance line is directly proportional to the concentration or the amount of atoms those undergo electronic excitation in the flame. Student, today we discuss how the instrument is constructed for measurement of the absorbance of a gaseous state atoms, that is the instrumentation of flame atomic absorption spectroscopy. The instrumentation of flame atomic absorption spectrophotometer is similar to flame atomic emission spectrophotometer. Only the additional radiation source is required. Therefore, the components of flame atomic absorption spectrophotometer are like this. Number one, a radiation source. Second one is nebulizer and burner system, that is a atomizer. Number third is the spectroscopic apparatus to isolate a resonance line of the analytic element from the source or from the flame, that requires a wavelength selector or a monochromator. Second one is photodetector, and third one is a electrical circuit for recording transmittance and absorbance. Therefore, here all these components are exactly similar to the components which we are studying in flame atomic emission spectrophotometer. Here, similar to flame atomic emission spectroscopy, flame atomic absorption spectroscopy also performed on a sample which is in a gaseous state. Therefore, here nebulizer burner system or atomizer system is required to convert that sample into the gaseous state atoms. These gaseous state atoms are excited by using their own resonance wavelength. In flame emission spectroscopy, the gaseous state atoms are excited by thermal energy, but in flame atomic absorption spectroscopy, the sample is converted into gaseous state atoms by thermal energy but excited by using their own resonance wavelength or a radiant power generated from the resonance line of the analyte element. Another component that is similar to flame emission spectrophotometer, that is a spectrophotometer, which involves the wavelength selector for isolation of a resonance line of the analyte element, photodetector to detect the intensity of that resonance line, and circuit for recording the transmittance and the absorbance. Therefore, here all these components are, that is nebulizer burner system means a integral burner, that is integral atomizer, and laminar flow burner or premix atomizer, that are the nebulizing system used in FES, exactly same in AES. Similarly, all other components are similar to FES. Therefore, here we have to discuss only the radiation source required in a atomic absorption spectrophotometry. The instrumentation of flame atomic absorption spectrophotometer is similar to flame atomic emission spectrophotometer. Only the additional radiation source is required. Therefore, the components of flame atomic absorption spectrophotometer are like this. Number one, a radiation source. Second one is nebulizer and burner system, that is a atomizer. Number third is the spectroscopic apparatus to isolate a resonance line of the analyte element from the source or from the flame, that requires a wavelength selector or a monochromator. Second one is photodetector, and third one is a electrical circuit for recording transmittance and absorbance. Therefore, here all these components are exactly similar to the components which we are studying in flame atomic emission spectrophotometer. Here, similar to flame atomic emission spectroscopy, flame atomic absorption spectroscopy also performed on a sample which is in a gaseous state. Therefore, here nebulizer burner system or atomizer system is required to convert that sample into the gaseous state atoms. These gaseous state atoms are excited by using their own resonance wavelength. In flame emission spectroscopy, the gaseous state atoms are excited by thermal energy. But in flame atomic absorption spectroscopy, the sample is converted into gaseous state atoms by thermal energy but excited by using their own resonance wavelength or a radiant power generated from the resonance line of the analyte element. Another component that is similar to flame emission spectrophotometer, that is a spectrophotometer, which involves the wavelength selector for isolation of a resonance line of the analyte element, photodetector to detect the intensity of that resonance line, and circuit for recording the transmittance and the absorbers. Therefore, here all these components are, that is nebulizer burner system means a integral burner, that is integral atomizer, and laminar flow burner or premix atomizer, that are the nebulizing system used in FES, exactly same in AES. Similarly, all other components are similar to FES. Therefore, here we have to discuss only the radiation source required in a atomic absorption spectrophotometry. The block diagram of flame atomic absorption spectrophotometer is nearly similar to the flame atomic emission spectrophotometer. Here a radiation source, that is a halo cathode lamp, is used as a radiation source. Halo cathode lamp is a radiation source. Radiation from this source is given onto the flame containing a sample. That is sample cell is a flame which is here a atomizer. That means here flame atomizer is used as a sample cell as well as it converts the sample into gaseous state. This is a nebulizer system. Nebulizer system, we know that there is inlet for fuel gas, then a inlet for oxidant and the sample solution. Therefore, here a oxidant and here a sample solution. That means similar nebulizer we studied in flame emission spectroscopy. Next component is monochromator. Monochromator, here this device isolate a resonance line of the sample from the source, and next component is detector. Here a photodetector like a photomultiplier tube is used as a detector. Finally, a amplifier and recording system is placed. This is the block diagram of flame atomic absorption spectrophotometer. This block diagram, this part is similar to a flame atomic emission spectrophotometry or spectrophotometer, but additional radiation source is required to construct a instrument of flame atomic absorption spectrophotometer. Here in this case, the radiation source, sample cell, monochromator and photodetector that are placed in a single axis, while sample introduction system or nebulizer system is away from the axis or perpendicular to axis, or recording system may not be in the axis. But all these four components, that is radiation source, flame or sample cell, monochromator and photodetector, are in a single axis. Therefore, when we have to write a question, what are the arrangement of the optical components in atomic absorption spectrum one is radiation source. Then next component is flame or atomizer, that is a sample cell. This is a sample cell. After that, the next component is monochromator, and then detector, and finally a recorder. Now if we compare the instrumentation of flame atomic absorption spectrophotometer with a molecular absorption spectrophotometer, in molecular absorption spectrophotometer, first of all there is radiation source, then there is monochromatic system, after that there is sample cell, then there is detector and recorder. In flame atomic absorption spectrophotometer, first of all there is radiation source, then sample cell, then a monochromator, then photodetector, and finally recorder. Now in this way the instrument of flame atomic absorption spectrophotometer is constructed. Now we discuss in detail the radiation source used in flame atomic absorption spectrophotometer. The radiation source which is used in atomic absorption spectrophotometry is classified into two types. Radiation source is classified into two types. First type is called as a continuum source. Continuum source, that is, gives the continuous radiations within a particular radiation band. That means here a continuum source that gives a radiation in a specific region of electromagnetic spectrum, and this source is useful for a qualitative analysis. Here a xenon arc lamp is used as a radiation source, continuum radiation source in atomic absorption spectrophotometer. Second type of radiation source is called as line source. Line source that emits only few lines of the analyte element, and therefore it is constructed from the analyte element itself. Line source in flame atomic absorption spectroscopy is a halo cathode lamp. Therefore, here we discuss the continuum source and line source which are useful in a atomic absorption spectrophotometry. The radiation source in atomic absorption spectrophotometer, first type is a continuum source. That is, a xenon arc lamp is used as a continuum source, while line source is a halo cathode lamp. First of all, we discuss the construction and working of xenon arc lamp. Xenon arc lamp that used as a continuum source, continuum radiation source in flame atomic absorption spectrophotometer. Continuum source is that emits broad band of radiations. These radiations can be useful for the qualitative analysis, that is identification purpose analysis of the atomic species present in the flame. Present in the flame. That means here, by means of continuum source, we can irradiate that sample with a bundle of wavelengths. A particular wavelength which is absorbed by that particular atomic species is its identity. Xenon arc lamp supplies wavelength from 200 to 700 nanometer. Therefore, here, when we irradiate sample or atomic species with the radiation in between this, a specific resonance line is absorbed by that atomic species, and that is the identity of that particular material present in the flame. We discuss here the construction of this xenon arc lamp. Xenon arc lamp is constructed as shown in figure. There is two graphite electrodes which are separated by a distance of 1.0 centimeter, and these are placed in a glass box containing a quad window. Here, these two electrodes are connected to a very high DC potential. This is a negative, positive. About 300 to 400 volt DC potential is applied across these two electrodes. Here these two are the graphite electrode. Inside this bulb there is xenon gas having pressure about 1 to 5 torr. That is 1 to 5 mm of Hg. This is a construction of a xenon arc lamp. Here a dispersing system, that is a prism is placed. Radiation from this prism get resolved into different wavelengths. By means of slit, a particular radiations are allowed towards the sample. This is the construction of a xenon arc lamp. Now we discuss the working of this lamp. How does it work? When 300 to 400 volt DC potential is applied across these two graphite electrodes, which are separated by a distance of 1 centimeter from each other. Here, with application of 300 to 400 volt DC potential, these two electrodes are momentarily brought in contact with each other, so that here the spark is generated, and during this a 5 to 15 ampere current is flowing through the circuit. Because of this, temperature inside the bulb reaches to, or temperature of this graphite increases to 4000 to 8000 Kelvin. Due to very high temperature here, the xenon gas undergo a electronic excitation. That is, xenon given in its excited state, means outermost electron of the xenon atom given to next excited state, and when it comes back to ground state level, that emits a radiation having a wavelength in between 200 to 700 nanometer. Now in this way, this xenon arc lamp is work. I repeat again this. With application of 300 to 400 DC potential across these two electrodes, graphite electrode, the graphite electrode are momentarily brought in contact with each other so that electric spark is generated here and a current of 5 to 15 ampere flows through the circuit. Because of this, the temperature of this electrode increases to very high. It reaches to 4000 to 8000 Kelvin. Because of this high temperature, xenon which is present inside this bulb undergo electronic transition, and when it comes back to its original ground state level, that emits a radiation having wavelength 200 to 700 nanometer. These radiations are then given on a prism monochromator where a dispersion of radiation is carried out and particular wavelength is isolated for a analysis purpose. Now in this way the working of this xenon arc lamp takes place. Now here advantage of this electrode, advantage of this source, we can use this source for analysis of many elements which absorbs the radiation within range 200 to 700 nanometer. Second advantage is that intensity of this line or intensity of this wavelength which is emitted by this xenon arc lamp is very high, and therefore here we can easily isolate that particular monochromatic radiation. Here the main disadvantage of this source is that the atomic absorption line of atomic species are very narrow. The bandwidth of the atomic species, bandwidth of the atomic absorption line of atomic species ranges from 0.03 to 0.005 nanometer. Therefore, here a very quality or highly sophisticated monochromatic system is required to isolate this line whose bandwidth is this much for identification purpose. Therefore, with a highly sophisticated monochromatic or dispersing system, we can use this source as a source for identification of the atomic species present in the sample. Student, now we discuss the second type of radiation source, that is called as a line source. Line source in flame atomic emission spectrophotometer is the halo cathode lamp. This halo cathode lamp is a line source used in atomic absorption spectrophotometry. Line source is constructed or it is invented by Alan Walsh in 1955. This line source is constructed from the analyte element, and therefore emits a lines of analyte element only. Therefore, here halo cathode lamp is constructed by using a analyte element. Cathode is made up of analyte element. Therefore, it emits the emission lines of the analyte element only. Therefore, it can be selectively used for analysis of particular analyte in presence of other. That means here suppose we have to determine copper in place of zinc, nickel, aluminium, and if we use copper halo cathode lamp, then we can measure the concentration of copper only. though zinc, nickel and aluminum may be present there. Because here resonance line of copper or emission line given by copper halo cathode lamp are absorbed by the copper present in the flame. And therefore here in presence of other impurities or interference material, we can easily determine particular analyte selectively by using this light source called as halo cathode lamp. Now we discuss how does it constructed. Construction of halo cathode lamp is like this. In this case, cathode is made up of a cylindrical analyte element. Here this is a glass sheet. This is again another glass sheet. Here this is another electrode. Both electrodes are kept in a evaporated glass bulb containing quad window. Therefore here this is a quad window. Quad window. This is a cylindrical cathode made up of analyte element. This is a glass sheet. This is tungsten anode. As it is anode means positive potential, it is cathode means negative potential. 300 to 400 volt DC potential is applied across this electrode. This is a glass shield and these are sealed in a material which is electrically resistant. Here this is a cathode made up of analyte element and this is an anode which is made up of tungsten material, tungsten metal, and inside this glass tube there is argon or neon gas of 1 to 5 torr pressure, that is 1 to 5 mm of Hg. This is a construction of halo cathode lamp. Halo cathode lamp is an important light source used in atomic absorption spectroscopy. In 1955 it is invented by Alan Walsh. The construction of halo cathode lamp is as shown in figure. It consisting of a cylindrical cathode made up of analyte element separated by another tungsten anode. These two are glass sealed, and here inside the glass bulb there is neon or argon gas of very low pressure. Now we discuss how this source work. Therefore, line source that uses limited number of lines which are required for the analyte element. With application of 300 to 400 volt DC potential across cathode and anode, the temperature of cathode 11,000 degree Kelvin, which makes the cylindrical cathode red hot and nearly 5 to 15 ampere current is flowing through the circuit. Due to very high temperature, xenon undergo a ionization process. Due to high temperature, argon undergo, because here we are using argon gas undergo ionization to argon cation, that is Ar gas gives Ar plus, also in gaseous state, plus electron. Here, as this argon undergo ionization, electrons are attracted towards this positively charged electrode, that is tungsten anode, and with a great velocity this argon cation strikes onto the wall of the cylindrical cathode. Due to this, with a great velocity, with a great energy, the argon cation strikes on the heated cathode, and that removes the gaseous state metal atoms from the cathode. Metal atoms from the cathode. Here, a atomization process takes place, that is, gaseous atoms of particular analyte element are obtained, and here these atoms undergo a thermal excitation. That is, metal atom dislodges from the halocathode lamp or removed from halocathode lamp, undergo a electronic transition to excited state, and when it comes back to ground state, that emits a radiation, which are the emission lines of the analyte element. Emission lines of metal, analyte metal present in the flame. That means here argon gas strikes on the cathode, that removes the metal atom in gaseous state. These metal atoms undergo a electronic excitation, and when come back to ground state level, that emits a radiation, which is a characteristic of the emission line of the analyte element. In this way, this halocathode lamp is work. In today's or in a modern era, about 40 to 45 halocathode lamps are available for analysis different element. Because here halocathode lamp is special halocathode lamp is required for analysis of special element. That means for analysis of copper halocathode lamp is required. For analysis of zinc halocathode lamp is required. Therefore, 40 to 45 types metal halocathode lamps are commercially available for analysis of different elements. Sometimes here coating of the alloy is carried out onto the inner wall of this halocathode lamp. Then that type of alloy type of halocathode lamp is useful for analysis of many elements. That means here single halocathode lamp containing a alloy material, that is alloy is a mixture of two or more metals. Therefore, this mixture allows the emission line of those elements. Therefore, we can determine all those elements using a single halocathode lamp. Therefore, alloy form of halocathode lamp is useful when the emission line or resonance line are not nearer to one another. That differs widely in their wavelength range, and those are determined by the alloy type of halocathode lamp. Student, this is all about the different types of source used in atomic absorption spectroscopy. With our today's discussion, you can find out the answers of following question. Number 1, what are the radiation source? What are the radiation source in atomic absorption spectroscopy? Second one, give construction and working of continuum source in AES, and number 3, give construction and working of line source in AES. Here you can find out the answers of this question from our today's discussion. With this, we stop here. Thanks for joining me. Keep learning. Happy learning.